This particular question is having you answer a whole slew of questions. Okay, so it's a lot of stuff stacking with this. Arguably the last one is probably the beginning, the first question you should be addressing. So let's walk through it. How do you know you have a chemical reaction? What evidence do you need to see? Change in phase, okay, is going to be the big one as far as lecture goes. What are the other ones? Permanent color change and heat change in energy. Okay, the color change and the change in energy are typically things that are not easy to go through and put on a lecture exam. Those would be things that would show up in a lab class. So here we're looking for changes in phase. Okay, so what are the formulas for each of those compounds? You get sodium chloride, said aqueous, yeah, plus aqueous lithium nitrate. So some things that you should be aware of if you aren't getting the symbols right. More or less, not a big deal. You do have to be a little bit careful with that, but if you're getting the symbols wrong, that might be something you need to review. Make sure you know your element symbols and perhaps more importantly, know your complex ions. Okay, those were all part of things that you should have learned and memorized and worked with in Unit 1 so that you can increase your speed with going through and solving questions. If we've got those as reactants, what type of chemical reaction would be expected? Okay, so what we're looking at is noticing the patterns within this. We've got a metal and a non-metal. Metal, non-metal. You could also look at it as a cation and anion as we navigate that, which suggests that we're going to run a double replacement. So we could initiate the double replacement. We'll have the lithium with the chloride. We'll have the sodium with the nitrate. Officially, we are responsible for ensuring that those are properly balanced. So if we're going to try and do this as an open-ended question where we had to provide all the context, yes, we'd go through and balance it. This question was multiple choice. We didn't need that information. So at least initiating the double replacement is probably all you needed to go through and do. If we go through to check the balancing, we should hopefully see that they are indeed balanced. So we don't have to stress about that. So we've got our products predicted. Should have color-coded that in blue. Okay, and then what are the special considerations for this particular reaction? When it comes to the double replacement reaction, you're responsible for predicting both the products and if a reaction happens. And we know that through the change in phase, which means you need to know your solubility rules. Okay, which is said a bit overzealously. It's not that you need to know them, you need to know how to use them. So you would go to the front of the exam, or in this scenario, if you don't have them memorized, which is fine, you would just go look up your solubility rules for these individual compounds. You would then go through and apply those solubility rules to each of your products to see what their phase was. Lithium is a group 1 metal. One of our rules is all group 1 metals are soluble, which means it comes in as aqueous. Sodium is also a group 1 metal, also going to come in as aqueous. Which then means I've now fully predicted everything and I can now go back to the original question, what evidence do we need for a chemical reaction? We need to see a change in phase. So we can look at the phases identified for each and every single one of our species and note they're all aqueous, which means did we get a change in phase? No. So is there a chemical reaction? No. Does that make sense? So you will encounter questions that stack content. Right? They build on that information. This is something that's going to continue to happen throughout your careers. In whatever field you're in, you're always expected to refer back to older content. Officially, this question is not a Unit 3 question because we haven't added anything that Unit 3 brings in. Unit 3 is all about quantification. So this is a review question going back to Unit 2 and saying how well can you apply that content. Make sense? So can I delete everything? Okay, if we delete everything, we should be able to see the answer choices underneath it. Okay, so we're looking at a no phase change occurs. That looks like A right out of the gate. All right. So sodium reacting with the nitrate as a statement from one of y'all. I don't really know what that means, because you could be saying sodium metal reacting with nitrate. Maybe you're saying the product, sodium nitrate. Okay, you're saying it's forming a solid, so that would be a good yes, except that sodium nitrate doesn't form a solid. Okay, and that falls back to those solubility rules. Kind of makes sense? So that little bit of a warm-up, do you guys have questions now? So we've got question 28. We've got a bunch of text to go through and read. Okay. Not always the case, but a lot of text can sometimes be irrelevant. So this is where you can go through and set up the work process that you know how to go through and do, and then see what happens. So as we scan through that, Superman, feature the new planet, noble gases are diatomic. How many liters of gaseous krypton? So we've got liters of krypton. Ooh, it's diatomic, so I should say Kr2. Okay, would be occupied by 0.33 moles at standard temperature and pressure. So 0.335 moles of our gaseous krypton. Whoops, krypton 2. So we really only have one piece of given information. Whoops. So let's just go ahead and drop that straight into the expression. Should that go in the numerator or the denominator? Why should it be the numerator? Yeah. Krypton should show up in our numerator in our answer, so starting with our moles of krypton in the numerator also makes sense. Okay? The given piece of information was just a single thing, which then means it's all going to be over 1. Is moles the same thing as liters? So what do you got to do? We got to do a conversion. Okay, how do we do that conversion? What do we want to have happen? We want our moles, krypton 2, to cancel out. So to cancel out, you need to drop that in the denominator. And what needs to appear in the numerator? Liters of our krypton. Do I know how to do that conversion?
Yes.
Yeah? What is it?
22.4 moles equals 1 liter. Is that right?
22.4 liters is equal to
1 mole.
1 mole. Okay. So we can now plug that information in, 22.4 liters and 1 mole. So far, so good? Do we have our answer? And this is where reading questions can sometimes bite you. If we go through and read through this, it says, a feature of this new planet is that all noble gases are diatomic. Okay, so it's not Kr, it's Kr2. Should that affect our overall result? Okay. So what this question is actually getting towards is what are the assumptions we make when we think about gases? So what are some of the assumptions we make when we look at a gas? What makes them ideal? What are the rules? They take up no volume. Okay? Which is why 22.4 liters can equal 1 mole. Okay? Because if I'm looking at a mole of, let's say, hydrogen gas versus a mole of radon, would I expect that to occupy a different volume? And that might be too abstract for you, so let's switch it up a little bit differently. I'm going to lean on you a little bit, Ashley. If we had 100 Ashleys around versus 100 me's, would we expect the same volume to be occupied? Why not? Different sizes. Is hydrogen a different size than radon? So would we expect them to occupy a different volume? Yes. And yet, does that expression say anything about what the gas is? No. Why not? What was one of our assumptions that we make when we talk about the ideal gas? They literally have no volume. So it does not matter the identity of the gas. It's irrelevant. Because they all take up no volume, period. So the idea of size becomes an irrelevant argument. And if you read this question and see that diatomic, you go, oh, well, it's got 2 atoms, therefore I need to factor that 2 atoms into this. No, you don't. It doesn't matter the amount of atoms. If it's a gas, it occupies no volume. Which means you're done. Enter it into the calculator, you have your answer. The fact that it's diatomic is a complete red herring. Kind of, sort of. Okay. There are not a lot of ways to ask about the assumptions made for the ideal gas. This happens to be one of them.
The exam is next week, right? Or is it this Wednesday?
The exam is this Wednesday.
Okay.
Yeah. This week. What? It's not next week. It's this week.
On the modules, it says it's the 16th.
We've got literally no content to talk about for a week. Oh, pen. We'll put that in the recording. So, for the sake of the recording, if you were paying attention to me, I was wrong. Your exam is not this week. It is next week. It is scheduled for the 16th. Is that officially the right day for Wednesday next week? 14, that sounds right. Okay. Which then takes us again to what questions do you have? So if we're going to look at 16, so we're given a solubility graph. Okay, and we have to kind of understand a little bit about what the graph goes through and shows. So what we're talking about is taking a mass. Okay, so this curve is really just a bunch of data points. We took the corresponding mass. So let's pick something that aligns. So at this point, whoa, come on. Okay, at that intersection, we took 200 grams of sugar. We added it to 100 milliliters of water, and then we heated it up to, well, in this case, we probably cooled it down to 20 degrees Celsius. When we did that, all the sugar dissolved. So that's what that point means. That curve is effectively our saturation curve, our saturated. Okay. If I'm under that curve, so let's drop to that blue point, what does that mean? Right? I have less sugar added into that than I could have. Right, which means I could add more. What we would call that blue point is then unsaturated. I haven't added enough. What happens if I move up to, say, the purple point? Okay. I now have more sugar in the solution than it should physically be able to take. That purple line is now supersaturated. All right? So if we now go back to the question, right, we have a solution containing 300 grams of sugar dissolved in 100 milliliters. The 100 milliliters comes from our question, so it's really just redundant. Water at 80 degrees Celsius. So we want to go to our curve. We want to find our 300 grams of sugar. So there's our 300 grams of sugar line. and we're at 80 degrees Celsius, where they intersect is what we're talking about. So where is that point? Which means it's unsaturated. That's it. All you're trying to do is interpret the graph based off the information given. Yes? Sure. Before we do that, how could we leverage this to do something interesting? Okay, so one thing that we could potentially do, which you may have done as a kid, is that we could take boiling water, so 100 degrees Celsius, and we could dissolve, what is that, close to 500 grams of sugar in it. So it all dissolves. I can then stick a stick into that solution, put a lid on it, and then I set it aside. Okay, ideally I cap it. Okay? What's going to happen when I set it aside? Temperature's going to drop. Okay? As it drops, it'll probably drop, we'll just say ballpark about 200. Okay, so it's going to go to about there. At that point, I'm now super saturated. There is more sugar in the solution than can physically fit within it. And if there's more sugar in there than it can fit, what does the solution do? It kicks that sugar out. Okay? And depending on the phases, talking about our solubilities, we could get different forms of separation. Since sugar is a solid, what does it do to kick it out? The sugar turns back into a solid. And what it's going to do is grab a hold of anything that's not water to form that solid. So it'll form sugar crystals on the sides of the glassware, and more importantly, it'll form it on the stick. So that once I've decided there's enough sugar crystals there, I can open it up and I can pull my stick out and I now have rock candy. So you've ever seen those sticks with weird sharp crystal? That's exactly what they went through and did. They just dissolved a bunch of sugar in water and they put a stick in it and then you paid $5 for it. Okay. They might have added some flavoring to make it taste better or maybe some coloring so it looks cooler, but that's all it is. Hooray. Okay, so we can manipulate that. It's going to cause things to shift around. And ultimately, that crystallization process is going to be made up of that difference. Because what it's going to do is try and reform that saturated solution so I could get 300 grams of sugar to crystallize out. Is that a question?
Yeah, I was going to ask, how would you answer number 26?
Okay, she had a question first, but then I'll add to that. What was your question?
15.
So what is the molarity of a 100 milliliter glucose solution that contains 10.0 grams of glucose, one with a molar mass of 180.18 grams per mole? When you read this, what are you being asked to solve for? Molarity. And as soon as you see the word molarity, what should you immediately write down? Moles over liters. I heard reference to a capital M. No, because capital M is not a useful unit system for us to convert with. Moles per liter is. Why do we write capital M? Because nobody likes fractions, including chemists. So we invented a new unit so that we didn't have to write out fractions on all of our solution containers. But if you're going to go through and manipulate it and run any calculations, you immediately need to convert it into a unit system that allows you to function. Okay, so what are we being asked for? We want the moles per liter. Moles of what? Glucose. Ain't always got time to write out glucose. Too many letters. We'll write out the formula. Oh, God, that's even worse. G. Okay? Pick anything you want to navigate that system so that you know what's going on with it. Okay? We've got a bunch of given information. Okay? And if we're following our patterns that we've talked about before, we could say we had, what? It was 100.0 milliliters of the solution. And we have 10.0 grams of our glucose. And we also have 180.18 grams of glucose per 1 mole of our glucose. So, what do we do? At this point, hopefully, it's boring. We do the exact same thing that we do every time. I want moles of G over liters. I go back to my given information. Does any of my given information give me a unit that matches what I want? Yeah? What color? Green, blue, or purple? Blue gives me grams of glucose. Is moles of, or grams of G the same thing as moles of G? Is grams of G the same thing as liters? Okay, so it is not wrong, but it's going to set you up in potentially a weird gray spot. Okay, so again, is there anything that what we want, does it appear in what we're given? I would argue the one in purple has moles in it. It has the moles where? And the denominator, is that where I want them? No, I want them in the numerator. So I can write moles of G here. I'm relating the moles of G to the grams of G because that's what that expression relates. It also gives me some numbers. That 180 is in the numerator, so I'm going to write it in the numerator. And I would be wrong because I don't write it based off of its location, numerator, or denominator. I write it based off of the unit it's tied to. That 180 is tied to grams. I'm going to put that 180.18 next to the grams. The number I'm going to write with the moles is 1 because that was how it was presented in my given information. This gets me moles of glucose. That's exactly what I wanted in the numerator. That's fantastic. But I've brought in grams of glucose. Do I want grams of glucose? No. So I need to do something else. And that same thought of needing to do something else, I don't see liters showing up in my expression yet either. So I've got two issues. Grams of glucose needs to disappear, and I need liters to appear. So, what should I do? Okay. Why do I want grams of glucose to be in the numerator? So the units cancel out. Do I know anything about the grams of glucose? I know I have 10.0 grams of glucose. That was from my given information. Is that all it supplied, or is that grams of glucose being related to something else? Does that blue thing say anything about moles of glucose? Is it tied to any other unit? No. What appears in the denominator? 1. What happens? My grams of glucose will cancel. That's fantastic. I didn't want grams of glucose. Do I have my answer? Nope, I'm still missing something. What am I missing? I need liters, and I need liters to appear in the denominator. Do I have the liters? No, what do I have? Milliliters. What is milliliters a measure of? Volume. What is liters a measure of? Volume. You mean the stuff that we talked about when we talked about our measurement units back in Unit 1 and Unit... Yeah, that's why we did that. So that we have that grouping. I need a volume unit to appear where? In the denominator, which means where should I place my green number? In the denominator. Okay. That's 100.0 milliliters of my solution. What shows up in the numerator? Look at the given information. What is it related to? What other unit is in the green box? SOLN. You mean the SOLN that's also already written into the expression? What other unit appears? None, which means what appears in the numerator? 1. Are we done? No? What's wrong? I don't want milliliters in my answer. So I need milliliters of solution to appear in the numerator so that it can cancel out. What do I want to appear? liters, and I want that to appear in the denominator. Do I know the conversion factor between milliliters and liters?
Yes.
Yeah? Dangerous question, but I'm going to ask it. What is it?
10 to the negative 3.
10 to the negative 3. Fantastic. Where do we place our power of 10? With the core unit. What's our core unit? Liters or milliliters? Liters. 10 to the negative 3. 1 goes with the milliliters. Right? What happens? I see you. Milliliters of solution cancel. What do we now have to do? Now we just do the calculation. We just solve. Put it into the calculator and we have our answer. Yes?
You have to put 10 to the negative third if you just put about 1 or 1,000 milliliters equals 1.
Okay. So can you put in 1,000? Well, if you do this, no, you can't.
Right.
That becomes the problem.
You can't
Okay.
put on the-
So you have to remember that if you're going to use 1,000, that it has to go with the milliliter unit. But you also have to remember that when you do kilogram, the 1,000 goes with the other unit. So you're memorizing 2 pieces of information. Can you do that? Yeah? Fire away. Do you screw it up? All I'm going to do is point at it and be like, remember when I told you not to do this, and this was a dumb thing that you were trained in your biology class and other science classes officially, because it's not just biology, that it was a stupid thing to tell you to do because it required multiple brain thoughts. Save your brain thought for critical information, not for how do you do a stupid conversion. That's my argument. Okay? So either one of those will work because they are mathematically and for all other purposes equivalent. It's just a preference on where you want it or what values you want to deal with. Okay? We went to the 1,000 because we don't like 10 to the powers, and we definitely don't like 10 to the negative powers. That's the only reason we did that. Okay? But we also, when we did that, did not have calculators. Right? You have calculators now, and if you're, because I know everybody grew up, at least I grew up, your math teacher, oh, you'll never have a calculator, with you at all times. Ta-da, that's wrong. Okay? And I would make the argument, if you don't have a calculator with you at all times, you've got bigger problems than how to enter something into a calculator. You're probably in a situation of doomsday environment, and you're probably looking for your next meal, not worrying about trying to divide by 10. Okay? That's where we're at within our technology. So, yes, you will always have a calculator. You should leverage it. As I say that, I know exceptions to that. MCAT doesn't let you take a calculator, so you have to be able to estimate things. So there are cases and there are instructors that refuse the allowance of calculators because they feel it's very important. Everybody's got opinions. Make sense? I want to throw one more thing out there that I'll mention, and I've seen on the internet. See if I can pull it off. I heard someone shout something about a formula, that probably molarity was equal to your number of moles divided by your number of liters. So if you could figure out your number of moles and then figure out your number of liters, you could put it into this formula. True, you can. Or, ta-da, there's no formula. Absolutely no need. Why did you memorize a formula? Okay, I can tell you why. Someone told you that it was powerful to have a formula because they didn't want to teach you how to do dimensional analysis appropriately. Right? The other one you'll see, and I get super irritated about this one too, these stupid triangles. So if you want to solve for moles, it's molarity times liters. If you want to solve for molarity, it's moles divided by liters. If you want to solve for liters, it's moles divided by molarity. So this triangle allows you to do this stupid formula system, okay, which is great if all you're trying to do is interconvert between those things. Okay? You already have a job. Okay? When you have a job, yes, algorithm the crap out of everything you do. Okay? If you don't have a job, you need to prove that you can make the algorithms. More soapboxing. We've got the internet. The internet gives us answers. If you go to a job and be like, yeah, I can do this job, I just have to Google it, they're not going to hire you. Okay? What they want for someone to do the job, particularly high-paying jobs, is to be able to think and reason instead of having to just Google the answer. And I'll throw extra salt at pharmacists. I've had lots of pharmacists come through and be like, oh yeah, I'm going to become a pharmacy person because they get paid tons of money. I was like, okay, well, why? They're like, oh, it's such an easy job. You just let the computer tell you how to do it. You just told me why I shouldn't be paying you money. You're not long in this world for having a good, high-paying job in pharmacy, if that's your reason for becoming a pharmacist. Just be aware. You can still become one. Sorry, I didn't mean to throw dash dreams and all, but be aware that field has got problems. Okay? Next question. Did I answer that one in enough detail, Karen?
Yes, thank you.
So, which of the following substances would be expected to remain a liquid at room temperature indefinitely? Okay, so this one's got a couple different things going on within it because it brings up this concept of vapor pressure, and most people probably glossed over that part of the discussion in the lecture videos, okay, assuming you watched the lecture videos. But let's lean into this a little bit because the phrasing of the question is trying to help you out. Okay, so I have a container, container, and I'm going to put a liquid inside it. What happens if I put that liquid open like that in a container on the bench? We're like, well, I don't know. If we've got water, what happens? It evaporates. So it doesn't stay a liquid. It will eventually turn into a gas. So when we're talking about our liquids, we've got officially an equilibrium, which we haven't talked about yet, but a backwards and forwards between the gas and the liquid. Okay? How do we know it goes backwards and forwards? It's less obvious in Arizona. It rains. When it rains, that's the gas state being like there's too much gas and it becomes a liquid. Okay? Or you see fog, that's this equilibrium. That's the reaction going from gas to liquid or from liquid to gas. It's all dependent on pretty much the same thing, and lots of different things control that. Okay? So if we're looking at this, we want the liquid to remain a liquid for as long as possible. That means no gas. Shouldn't have put the no there. Okay? I want no gas or I want minimal gas. Okay? It then brings in this concept of vapor pressure. Well, what is pressure? When is pressure? Chem 130. Not yet. When is pressure a thing? You're starting to lead into the vapor pressure and all that, and I don't even care about it. When do I care about pressure? Let's try it this way. We've talked about solids, right? We talked about liquids, and we talked about aqueous. And all the times that we talked about those, did we talk about pressure? No. Why not? When is pressure? Gases. Okay? So if we're looking at these numbers, those numbers represent gas. And if you have a bigger number, what does that mean? More gas. I want no gas. So what number do I want? I want the smallest possible number. There's my answer. Okay? You can make it a whole lot fancier and get into the meaning of vapor pressure and all that, but you don't need to. Push to some of the simplest aspects that you know and leverage that information to get you to your proper answer. Does that make sense? Does that help, Hank? So the vapor pressure is the amount of pressure above a liquid. So it's actually telling you how much gas is there. So if you have a really big number, there's lots of gas above it, which is why if you've gone into, let's go with a gas station, there's a gas station smell. Why is there a gas station smell? Because when people transfer the gasoline back and forth from the hose, they're spilling a little bit. That spill of liquid turns into a gas relatively quickly, and that's what you're smelling. Think back to the nose lab that we did in Chem 130 in our labs, right? Right? You could smell things. The things that we were smelling were all based off of liquids. Why? We had to get a small amount of that liquid into the gas state so that we could smell it. Right? But if you smell a solid object, you don't smell anything. Why not? There's nothing in the gas state to make it into our nose. Right? So the only things you can smell are the things that make it into your nose. That's, for the most part, going to be gases. It is a rare circumstance to get other phases into your nose. We'll leave it at that. Kind of makes sense? This is also why ethanol, you can get flaming shots because it's producing a gas above it and you can ignite that. Other questions? For the record, finding out that the exam is next week actually makes me feel a little better too. So I was like, oh, I haven't gone into the thing to provide comments on whether it was right or wrong. But I've got more time. So, best to differentiate between an ionic bond and a covalent bond. How do you know you have an ionic bond? So a metal and a nonmetal. How do you know you have a covalent bond? A nonmetal and a nonmetal. So ultimately the thing that differentiates this is metallic character. The more likely we have a metal, the more metallic character we are, the more likely we have an ionic bond. So we just look for the thing that says metallic character, and we come up empty. Right? What is metallic character? So we could talk about metals' properties, but that's not our metallic character. Right? If we're looking at these as structures, we've got a bond between a metal and a nonmetal. And we've got a bond between a nonmetal and a nonmetal. How are those bonds different? How are those bonds different?
They're different types.
So they're different types, metals versus nonmetals, but we don't get an answer choice that's referencing any of that.
The ionic bonds are attracted this covalent bond.
Okay, so there's an interesting idea. In our ionic bonds, they're electrostatic. So if we looked at an example and we had sodium and chloride, what would you tell me about the sodium? The sodium would be positively charged, and the chloride would be negatively charged. How did the chloride become negatively charged? It starts neutral. What did it do? It had to gain electrons. Where did it gain electrons from? It took the electrons from that bond. This is called not sharing of electrons. That's how we get ionic bonds. Right? So is there a way to describe how one element would take electrons from another element? That is literally the definition of electronegativity. That's it. Okay? The rest of these things are ultimately going to be very, very specific cases that you could make true. Okay? Difference in size. The size is ultimately kind of irrelevant. I can bond iodine to carbon. Iodine's very large. Carbon's very small. That's a difference in size. I could also bond carbon to carbon. There's no difference in size. Right? And in all of those cases, both big and no difference, I'm seeing non-metal to non-metal. So the size doesn't help us out. The number of bonds. The number of bonds is just an artifact of trying to achieve octets, a la Lewis structure. Right? The difference in atoms. That's one that I've gotten a lot of people going on. Well, but sodium to chloride are different atoms, and therefore it's an ionic bond. And when I look at carbon to carbon, well, that's a covalent bond because they're the same atom. Well, what about carbon to oxygen? That's a difference in atoms. Or even carbon to carbon. They're the same atoms. There is no way for me to decide whether I have an ionic bond or a covalent bond just because I have different atoms or the same atoms. It doesn't differentiate. Right? Solubility. Solubility becomes a gray one because we can dissolve salts in water. Right? In fact, for this counterexample, we can actually push to a plot we already looked at. Oh, I don't remember which question it was. There it is. We can dissolve salt in water, right? Salt dissolves in water a lot. Right? That's an ionic bond. Sugar dissolves in water even more than salt. And it's a covalent bond. Right? Well, but then covalent bonds are always dissolving more in water than ionic bonds. Oil is a covalent compound, also does not mix in water. Right? Even less than that is for salt. Right? So what this is really pushing at is, do you understand the definition between the different bond types? Right? And it comes back to electronegativity, and it becomes huge, particularly for anybody that needs more chemistry. Right? And if you're in even the nursing fields, I would argue you're going to talk a lot about biology and things along those lines. Almost all of those are talking about different bond types. Those bond types are all based off of differences in electronegativity. So it becomes a really, really important concept. It's also going to show up in our next unit, which I thought was going to be next week, but clearly I'm an idiot. Next question. And just because someone was kind enough to provide an answer, officially no explanation. So by the way, no explanation means no response from me. But it's giving us a place to kind of leverage this. We're talking about typically increases the solubility of a gas in a liquid solvent, and their suggestion was increasing the temperature. I can tell you exactly why they wanted to say, well, potentially exactly why. What happens to the solubility of salt and sugar when I increase the temperature? More dissolves. Right? Even for the salt, it's a subtle change, but it is increasing. Right? So if we increase temperature, things dissolve. Right? And that makes sense for the answer they've supplied. However, we have to be really careful to nail down what we're talking about. And what do I mean by that? Where'd it go? 22. Okay. To start this off, what I want to do is have a quick conversation and review backwards towards arguably Unit 1. I'm going to have 3 boxes, and I would draw these arrows in between. What do you think should be in these 3 boxes? Any guesses? Good guess. Dang. A little bit crude. Which box do you think is the gas? Which one do you think is the solid? Okay. This one does become a little bit challenging, but if you're saying the far right is the gas, more than likely we're talking about this one is the solid and this one is the liquid. One of the things you might note is it's really hard to tell the difference between the solid and the liquid, right? Right. And that's ultimately because they're taking up very similar volumes. Right? But we've changed their ability to move. So in the liquid, it's going to be a little bit more disorganized. It has a little bit more motion. This is why when we look at liquids, they can move around. But if I took 2 glass containers okay, and had solid water in one and liquid water in the other, and we just didn't touch them, it would be really hard to differentiate them until we touched them to see the motion associated with the liquid. Right? Okay. So if we're talking about these transitions, what is allowing any of these transitions? What happens? How do I get the solid to turn into a liquid? What do I got to do? Okay, I got to add heat. How do I get the liquid to turn into a gas? Okay, I add heat. Okay, so that's going to be useful enough for this first part. If we're talking about increasing the temperature, particularly with sugar and salt, what phase are sugar and salt? Those are solids. Right? It's the way you can pour them and you would dissolve them in things. Right? And so if I'm thinking about the solid, I'm trying to get the solid to look kind of like the liquid. Right? And we technically have this fourth phase of aqueous, which is outside this realm, but the aqueous now has a liquid with stuff dissolved in it, which is why it's not really a phase. Right? Or it doesn't hit the main phase tree. And if I'm talking about dissolving the solid into the liquid, what do I want to do with my heat? I'm trying to turn the solid into a liquid. What should I do? I should heat it up. Why do I want to heat it up? I want those particles to move more. And the hotter it is, the more they move. That makes a lot of sense. Look at the gas. The gas is already moving a whole lot. If I add more heat, what's it going to do? Move even more. What do I want to do to it to make that gas turn into the liquid? I need to slow it down, not speed it up. And so by increasing the temperature, what happens? I get more gas, not less gas. Okay, so to get that gas to dissolve, I don't want to add heat. Have you already observed this? Some people are like, yeah, I observed it rather painfully. You ever taken a soda and left it in your car by accident, like a sealed one, closed soda, particularly in the middle of the summer? Some people are laughing because they've heard stories. What happens to the soda in the middle of the summer? It explodes. Why?
Gas builds.
When we increased the heat, all the gas that was dissolved into your soda no longer wants to be dissolved. You're looking at a closed container with a rapidly expanding gas known as a bomb, which is why it explodes and sprays soda all over your car. Okay? Which is not particularly fun to come back to. That's why I don't drink soda. Other reasons, but I figured that's a nice one.
Doesn't that also happen if you put it in the freezer?
It also explodes when you put it in the freezer, though, which is an interesting question. Is that because the gas is expanding? No, what's happening there? There you're falling into a trap of what water does. Water is a very tricky substance. And water, solid water, does what? It expands. How do we know it expands? Where do you see solid water when you put it into liquid water? On the surface. It floats. It's less dense because what are you doing with that water? You're spreading it across a larger volume. So that same mass is now spread across a larger volume. Division gets in there and your density decreases. Because your density is lower, the ice floats. Why does that become a problem? If you're freezing a small container, that ice wants to expand its volume. It can't unless it breaks open the container. So you're getting it for a slightly different reason. Okay? If we go back to the question at hand, I want the gas to go into the liquid. So how do I turn the gas into a liquid? Okay. One option would be to remove the heat. I want to cool it down. As I cool it down, those gas particles slow down. They have nowhere else to go, and they can make it into the liquid state. Okay? That could help. What else could I do? How else could I force those gas particles to get into that liquid state? I've got a piston and I can push down on it. Okay, by pushing down on it, I'm decreasing the volume, which increases the pressure. So if I'm trying to get a gas to go into the liquid state, I can decrease the temperature and I can increase the pressure. Both of those things will help force the gas into the liquid state, okay? Which we've also seen, because if you open up a soda can, what does it do? Psst. What's happening? You've changed the pressure. You've decreased the pressure by allowing that air out, which is why the air is suddenly moving upwards out of the can or out of the soda. So again, you can leverage that information if you slow your way down through it. Make sense? Whose question? Is it you? You good? Yeah. Other questions?
Can we answer the D or F?
D, decrease the temperature, yes.
On the next active chem, question 1.
I was not prepared for that. So this one can be a bit tricky, so let's slowly kind of walk through it. When we're talking about gases, one of the most common things that I would do is pull everything out of the question and start to use kind of symbols for it. So right away, I have a balloon at 30 degrees Celsius. Celsius is a measure of temperature. So I have a temperature of 30.0 degrees Celsius. Okay. It has a volume of 22, or those numbers, 222 milliliters. If the temperature is increased, I'm changing the temperature now. So that would actually make me go back and want to put different numbers in here, because that T1 and V1 are now at the constant condition. Okay, and it says I'm going to change the temperature, T2, to 53.1 degrees Celsius. Okay, it then also tells me the pressure is constant. So I'm going to come back to that one. What's the new volume? Okay, in milliliters. There are a couple different ways to go through and do this one depending on what stuff you've got memorized. Okay, what we're looking at here is a gas. We've got pressure, volume, temperature, so we got a bunch of different kind of moving pieces within this. Gases have been studied for a long time, and they made lots of observations. Each scientist that made a particular observation got to attach a name to it. So you get Charles' law, Boyle's law, Henry's law. There's a bunch of frickin' names in scientists. Okay? Generally speaking, I do like to appreciate and acknowledge individual scientists' contributions. However, when it comes to gases, for whatever reason, I say no. Okay? And I, quite frankly, don't care. And it's ultimately because I think I got pressured into trying to memorize what each of those individual scientists' names were and what they discovered. And it was way too difficult for me to go through and do because I just suck at memorization. Okay? So instead, what I would go through and do is leverage the ideal gas law. Okay? The ideal gas law is what summarizes all of them. They all go into one pot. So why should I memorize a bunch of individual things when I can memorize one thing? That one thing is PV equals nRT, also known as Pivnert. Okay? Stupid anecdotal stories in the videos. Okay? And what I would do with that immediately is I would rearrange that into a more useful expression that I hopefully don't screw up right now. PV over NT. Okay? And the reason why that expression is useful is R is a constant. So it doesn't matter if I change temperatures or anything else or move to different conditions, R will always come out to be the exact same value. And that's what I'm going to go through and leverage to solve this question. Okay? What do I mean by that? Well, if I set up my expression using Pivnert, let's go with blue, pressure at conditions 1 times the volumes at conditions 1 divided by the moles at condition 1 times the temperature at condition 1. All of that equals a constant. That constant also happens to be equal to the pressure at conditions 2, volume at conditions 2, moles at conditions 2, temperature, at conditions 2. Okay? That has a whole lot of crap floating within it. And ultimately what we're looking at here is a rather complicated form of algebra. Okay? Sort of. I would argue most of our conversions were more complicated algebra forms than this. Okay? But now what we've got to do is just start subbing things in. We know temperature 1, we know volume 1. Great, we could solve those. We could do temperature 2. Volume 2 I don't know, so I could go through and solve that or plug that into this expression. Before I get too excited about plugging things in, hopefully what you notice is that we're missing some critical pieces of information. I have no idea what P1 is, P2 is, N1 or N2. Okay? So for some clarification, P stands for pressure and N stands for the number of moles. That's where the N is coming from. Okay? So if I don't have those numbers, how could I possibly go through and solve this? We have a balloon, okay, that has this volume. The temperature is increased. Did I blow air into it? Did I suck air out of it? No, which means what happened to the number of particles? It stayed the same. I didn't change them, which means N1 equals N2. Okay. The other part of this sentence that it reads through, and the pressure remains constant, which means P1 equals P2. So now I could start to go through and sub some information in. If I say P1 is equal to P2, so this is now P2, right? N1 was equal to N2, so this is now N2. What can I do with my P2s? They can cancel. If I divide both sides by P2, P2 cancels out, so that's gone from my expression. What can I do with my N2s? Cancel. Multiply both sides by N2. Gone from the expression. And this now leaves me with this expression. If I go back to my given information, I was given 3 values, and I'm asked for 1, which means I could now rearrange and I can solve for this. If I want V2, V2 will equal V1 over T1 times T2. Okay. Now it is mostly a plug and chug. And everything should work out. Okay. Why do I say mostly? Where did all this work come from? It wasn't from my brain. There was one part that came from my brain. What was that? I didn't hear what you said. Came from Pivnert. Pivnert admittedly came from my brain, so I need to know that. But ultimately, that's what set me up with all of that information. Why does that become valuable or important? Well, in Pivnert, we have to understand some of the conditions that make that equation true. And one of those conditions is particularly relevant when we talk about temperature. The temperature in Pivnert must be in units of Kelvin. If I'm not in units of Kelvin, that equation doesn't work. What does that mean for me? When I now go through and I have my V2, which is V1 over T1 times T2, I have to ensure that my T1 and my T2 are in units of Kelvin. Conveniently, we've discussed how to convert degrees Celsius into kelvins, right? Yes, we have. And how do we do that? You add 273. Once you account for that extra mathematical step, the rest falls into place and you're fine. Okay. Is there another way to do it? Yeah, if you've memorized, I'm going to say it's Charles's law. This is Charles's law. I honestly don't know if it's Charles's law, but this is one of those named laws, the relationship between volume and temperature. So if you knew that law, ta-da, you've got your expression, you could now go through and solve. Okay? If you don't know that law, then you'd better know Pivnert to be able to derive it. Okay? And since, again, I never bothered to memorize those gas names, I just went with Pivnert. Pivnert allows you to do it all. Make sense? Okay. Within this active homework, you will get a bunch of questions pushing you into what these things are, dealing with Pivnert and manipulating it. The biggest thing to remember is that R is a constant. It will always be a constant. So you can set up fancy expressions like this to solve for an unknown variable. Questions about what's up there?
So, when you move to T2, are you multiplying V1 over T1 by T2, like you're multiplying that whole fraction?
If that helps.
That helps.
Yeah, that's one that I get lazy on. In conversions, for whatever reason, I'm rock solid in dropping something under it for one, but gas laws, I just don't care. With that, if you couldn't tell, we are at time, so if you have other questions, you can come up and ask. And we will not have an exam on Wednesday. Okay? This Wednesday.